Good evening, everyone. Please, am I audible? Can I be heard, please?
Yes, please.
All right, all right, all right. So I think we can start already. So to start, we would first have a quick recap. I think I would really wish that we end today's session at least recover something significant and key maps, and then if we're able to do that, then we can see that we are now to things with what we are doing so far. So but first let us have a quick recap of what we did last week. I think someone was requesting that we do a brief recap before we commence. So let's do that quickly. Okay, so last week we looked at basic circuits, we looked at logic gates, we looked at Boolean expression and functions, we looked at how to draw a logic gate from a function and how to convert your logic gate diagram to a function. Please, a second. Okay, sorry. So we looked at how to convert our diagram into a function. And these things are very, very important for us to understand, especially considering the fact that our lecturer treats it as we've already done that in 102. So, all right, so let us quickly solve this. I think I gave this as an assignment for individual trials. So probably if you were able to try it, you can let us know what you had for the function. Um, okay, so please, did anybody try working this up? If someone did, you can call out your function and then we see whether it's correct or not. Please, can I be heard, please? All right, all right. So, okay. Uh, okay. Please, I believe you can see my screen.
Yes, we can see your screen.
Okay. I think I saw a comment from someone saying I should share my screen. So let's solve this. Okay, let's solve this together and let's see what we are going to get. So I stated during the last session that if you are solving something like this, or if you are working something like this, the first thing you are supposed to ask yourself is what kind of logic gates are we using here, or were used in that particular section. So here we can see this is an AND gate, right? And why do we say this is an AND gate? We said AND gates typically looks like this. They take at least two inputs, two or more inputs, and then return an output. And usually the bar is vertical. Okay. So let me erase that. And then we said that for all gates, it's something like this. This side is a little bit, it has a curved structure, right? And then it takes at least two inputs, returns an output also. And then we said that for a NOT gate is a buffer gate, right? But it negates its input. So this is a buffer gate. We put a circle in front of the buffer gate to denote a NOT gate. So you can basically just look at the symbol and then tell which type of gates we are using here. Okay. So if you look at the first symbol, you can obviously tell that this is an AND gate. Okay. So you look at this symbol, you know this is an AND gate. You look at this symbol, you know this is an AND gate. You look at this symbol, you know this is an OR gates. So this is the first and most important thing you have to do to identify the type of gates that we are using. But then when we come to our first AND gates, we have, please, I'm coming. Joel. So you have two inputs here, your X, and then processed with an AND logic. Okay, so what does the AND logic tells us? It tells us that if you have two inputs, X and Y, your output will be X dot Y, right? So this is the what the AND logic tells us. So we know that the output of this particular gate here is going to be X, Y. And we are going to pass on the output of this particular gate here as the input or as our first input. We know the second gate here takes three inputs. And the first input is the output of this particular logic gate right here. Okay. So whatever we are going to get for this logic gate will be passed on as an input for this logic gate right here. That is the first input for this logic gate right here. Okay. So we know that the second input for this logic gate has already been given as Z. So Z will be passed on as the second input. And we know the third input is X bar. So we are going to pass on X bar as the, or X prime as the input or as the third input for this particular logic gate. So we are going to have our first input being XY, our second input being Z, and our third input being X bar. And we are going to process these three inputs with the AND logic. And what does the AND logic tells us? It tells us that if we have the input XY, Z, and X bar, then the output is going to be X, Y, XY dot Z dot X bar right here. Please, are we together? And then we have the third, and then we have the third logic gate here. The first input is X, the second input is Y bar, the third input is Z bar. So we are using the AND logic to process these three inputs. And the AND logic tells us that if we have X, Y bar, and Z bar, the output is going to be X, dot y bar dot z bar. Okay, and then we are going to pass on that input as we are going to pass on the output here as the input for this logic gate, as a third input for this logic gate. So we have x y bar z bar, okay, or z bar. Let me put it like that. So we have our three inputs ready for our last logic gate here. You can see that our last logic gate here is an OR logic gate. So we know all logic gates, when you give it three inputs, the output is going to be an SOP, that is the summation of all the individual logic gates we have here. Okay, so the reason why I said it's an SOP is because we realize that all the previous logic gates were AND gates, right? So they literally found the products of its inputs. So the last logic gate is an OR gate, which finds the sum of its inputs. So that means that this last logic gate finds the sum of the products of these three logic gates. So the output of this logic gate is going to be the function W plus X, Y, Z, X bar, okay, plus X, Y bar, Z bar. All right, so this is going to be the most likely output of this logic gate. Please, does anyone have any question about this? Or if there is anything here anything that confuses you, you can voice it out. Or probably if you have a different answer, you can let us know, then we talk it out.
Hello, good evening. Good evening. Can I be heard? Good evening.
Um, please, are you all okay with what we did?
Good evening.
Yes, sir.
I'm saying that where I am is very noisy, but I placed what I worked on in the IT Masters group. So
Oh,
I don't know if you
okay.
can quickly check it out for and see. Thank
All
you.
right, so let me. All right, you're welcome, sir. So let me check it out. Okay. All right, so I think our boss went further to simplify the answer. That's perfect. That's perfect. That's perfect. That's perfect. Okay, so I think that's perfectly done. That's perfectly done. That's perfectly done. All right, so that's even going a step further. Okay. So please, we can all refer back to the to Mr. Freeman's solution, which is on the platform. Okay. Also, thank you very much, Sim. All right, so we can now progress to today's theme. So we ended at, I think we looked at SOP expressions and P. Please, I'm coming. Okay, please. I'm sorry for the delay. So let's continue. So we looked at SOP expressions and then POS expressions. Okay, so now let's look at how to identify what mean terms are, and then how to identify the mean terms of an SOP expression. Okay, so I'm going to do this very fast so that we can go straight to what we are supposed to do today. So assuming you have an expression like x plus y, okay. No, let me not use this expression. I think this will be much more of a max 10. So let me use, let's say x y plus, let's use x bar y, okay, plus x y z. I believe we would all agree that this is an SOP expression, right? So it sounds different product terms. Okay, so I believe by now, as of now, we all understand what product term means. This sounds different product term. So if you're asked to find the mean terms, you find mean terms for SOP expressions, and we find max terms for POS expressions. Okay, so if you are asked to what mean terms are basically the product terms that has all the variables in the expression present, okay, either in its raw form or in its complement form. This is what we mean, okay. So assuming this is your expression, your expression, we said that when you take every expression, you have something you call variables. Variables are the set of all unique members of an expression, okay? Whether bar or not, we don't consider bar, we just take the raw expression, because if you say y bar is actually y, but we are taking the complement of it. So the actual variable here is y, not y bar, okay? So if you take this actual expression here, it has three main variables. The variables are x, y, and z, right? These are the three main variables of this expression. Oh, goodness. Yeah, so let's continue. So these are the main variables of this expression, right? And then we also have something we call literals. Please, let's understand the difference between variables and literals. Literals refers to all members of an expression, whether you have the same variable repeating or not. We still consider it as a separate literal. For instance, you see this product term here. This product term contains two literals, okay, which is x and y. This product term here also contains two literals, x and y bar. And this product term here contains three literals, okay? So if you add 2 to 2, you have 4. 4 plus 3, you have 7, okay? So this expression here has a total of 7 literals, but 3 variables, okay? So if you are finding the the mean term, okay, the mean term of this SOP, what you are doing is that you want to look at the specific product term that has all members of the variables present. So what are variables? X, Y, and Z. So we come and look at the expression. Which product term has all members of our variables present? We have this right here. Okay, that is X, Y, Z. So we say this particular term here is a mean term of our expression. Okay, so we just look for the expression that has all members present, whether complemented or not. Assuming this was to be X bar Y and then Z bar, we will still say that this expression here, that is X, Y, Z bar, is our mean term or is a mean term of our expression. And when we are talking about our max term, we are talking about a POS expression. Let's say X, I explain this. Let's say X plus Y plus X bar plus Y plus Z bar. Okay, let me add bar plus X Z. Okay, so we have this right here, and let's do this S plus Z. We all agree that this right here is a POS expression, right? Why is it a POS expression, which is a product of sum? Because you can see that all the terms here are sum terms. This particular term here is finding the sum of X and Y, so it's a sum term. This particular term here is finding the sum of X bar plus Y, X bar, Y, and Z, so it's a sum term. This particular term here is finding the sum of X and Z, so it's also a sum term. And we are now finding, we are now finding the product, please forgive me. So to have a POS, we have to find the product, okay, of all our sum terms, not the sum. Okay, so forgive me, please. So we are now finding the product of all our individual sum terms. The resulting expression will be a product of sum expression. And for product of sum expressions, we find max terms, just as we find min terms for sum of product expressions. Okay, so we have our max term will be the sum term that has all members of the expression present, okay, or that has all variables in our expression present. So what are the set of all unique variables in our expression? We have X, Y, and Z, right? So if we want to find our max term, we'll circle out this particular expression here as the max term of this particular expression. Okay, so that is the mean term, that is our max term. As we move forward in the coming sessions, we are going to use this more. So you just have to know what it is, and then as we go forward, you will learn or we'll look at their applications. So let me refresh the screen. Okay, so during our last session, we looked at we also started simplification of Boolean expressions, right? We said Boolean expressions can be simplified. So you would realize that sometimes you might have very complex expressions, but look, if you take their complex expressions, you can just break it down to a very simple expression, which means that they are very easy to implement as compared to having a very complex expression. Okay, what am I writing? All right, so we just want to simplify our learn how to simplify our Boolean expressions. And look, if you want to simplify Boolean expressions, there are two different ways to go around it. You can just decide to use your Boolean laws, okay? So we have our Boolean laws. Boolean laws are just derived from our truth table. So it just represents as in how you can, you know, if you go back to high school, you remember we have algebraic things like algebraic expressions. You have to find ways and means to manipulate the expressions and then break it down and then simplify it into a form that is much easier to comprehend. It's just something similar. Or if you remember something like indices, you know, you have laws. So you want to manipulate the expression so that at the end of the day, you can just substitute and stuff, eliminate and make everything look simpler. Okay, so that is just what we are attempting to do here. So we have our Boolean laws, or we can also use our K-maps, which is our Karnaugh maps. Okay, so let us look at our Boolean laws. I'm going to take my time and then we are going to go through this thoroughly because this is very, very important. You can simplify all right, but look, if you end up getting your final answer wrong, everything you are going to do with it will be wrong. If you're asked to draw a logic circuit for that, it's the final circuit will not produce your intended output. Whatever you do with it would be wrong. So for instance, if let's say the final answer is A bar plus B, and then you end up getting A plus B, okay, out of a wrong application of the laws, you would realize that the output this will return will not be the same as the output this will return. Let's test this, okay? So assuming we have A to be 1, right? A to be 1 and then B to be 1 as our input combination. Let us compare this and this. You have A being 1. The complement of 1 or the inverted form of 1 is 0, okay? So you have 0 plus 1, okay? And then right here you have 1 plus 1. So here you might end up getting it correct. That is 1. This is 1. 0 plus 1, you get 1. But assuming your input is 0 and 0, 0 and 0, 0 complement or the inverted form of 0 is 1, right? So you have 1 plus, your B is also 0, so plus 0. You end up getting a 1. But if you take 0 plus 0, the result is a 0. So you see that the output of this here is not the same as this here. So it's very, very necessary that you're able to simplify right. Okay, so let us look at the laws and their applications. So when we are looking at the laws, we have the AND laws. Okay, so the AND gate laws, and then we have the OR, and then we have De Morgan's law. So let's look at the AND. So when we are looking at the laws for AND, we are saying that if we have, I will not really use the terminologies because I don't really, for those who have not yet gone through them, it would complicate everything, okay? But let's make it simple. If you have two inputs that are the same, okay, and then you are performing that particular operation using an AND operator, we are saying that your outputs will be the same as any of your inputs. And this is the proof for that. Assuming you have an input 1 or 1, the output of 1 or 1 and 1 will be 1 because you said that the AND operator represents presents or outputs a true if both inputs are true. Okay, so here realize that both inputs are true, so your output of course will be true. So you can see that your A and A will give you A, right? Assuming your inputs are also 0 and 0, your output is going to be 0 because you said the AND operator only returns a true if both inputs are true. So if at least one input is, if even one input is false, the output is also going to be false, okay? So that is the justification for this here. And then when you come to or, you are saying that A or A or A is also going to give you A or A is also going to give you your A, which is the same as your input. Okay, so looking at this, if you have 1 or 1, we said the OR gate returns a true if at least one of its input is true, right? So 1 or 1 would return a 1. Okay, and then we have 0 or 0 will return a 0, right? Yeah, so we'll return a 0 because it will the OR gate only returns a true value, okay, or returns true when one of its inputs is true. In this case, we have none of our inputs being true. Yes, please.
It's Isaac.
Yes, sir.
The AND gate, the law. That law, I don't understand. Can you please explain it better for me?
Please, are you talking about this?
The AND one. No, the previous one. The one that you.
The AND one. Okay, so we are saying that if you have two inputs which are the same, okay, so two inputs which are the same, we know inputs can only exist in the form 1 and 0, right? So
Yeah.
our combination of inputs that can be the same can be 1 and 1, 0 and 0, right? These are the set of all possible inputs that has that are the same. Okay, so you have 1 and 1. The AND rule, okay, or the AND law is saying that we will only return a 1. I think we looked at, we illustrated that with the circuit the last time. So it only returns 1 if both inputs are true. Okay, so it will only return what's true if both inputs are true. So you have 1 and 1 would give you 1 because both inputs are true. Okay, so when you take 0 and 0, the criteria we are looking for here is that both inputs should be true in order for our output to be true, to also return true. So if even one input is not true, it means our output will be false. I don't know if you're getting me. So if this was to be, let's say 1, 0, that is still going to return a 0. Or let's say 0, 1 is still going to return a 0. Because we need both of our inputs to be 1 for our output to also be 1. So that means 0 and 0 is also going to return a 0 for us.
Okay. What of 0 and 1?
Set what of 0 and 1 here? Okay. Yeah. So the reason why this set of input is not valid for our scenario is that, look, if you look at the law is saying A and A. I don't know if you're getting me. That means that the two inputs must be the same. I don't know if you're getting me. 0 and 1 are different. We can say A and B for 0 and 1, but you cannot say A and A. Either A and A, B and B, but not. Okay. Yeah, so the law only works, the law only applies to instances like this. When you are dealing with 1 and 1, and then 0 and 0. Those are the specific cases that the law addresses.
Okay.
Okay.
Thank you for that.
You're welcome, sir. So we are also saying for AND that if we have A multiplied by, okay, please, multiplied by in quotes again, okay. So if you take A and A bar, okay, or A and A complement, then the second law for AND is saying that our result is going to be 0. Okay. So this is what we mean. We know that AND has to return a true only when both inputs are true, right? But now we have a scenario where one input is true. If the first input is true, the second cannot be true because the second input is the opposite of the first input. So if the first input is 1, the second input will be 0. And if the first input is 0, the second input will be 1. There is no case for these two inputs, that is A and A bar, where we will get 1, 1. No, because the second one, A bar, is a complement of the first input, so it's rather becomes 0. I don't know if you're getting me. So I'm saying that assuming that our A is 0, we are going to have A here being 1, and A bar is going to be A is going to be 0, and then A bar is going to be the inverted form of 0, which is 1. Okay, so if you have these two scenarios, 1 and 0, we know AND only returns true if both inputs are true. So automatically this will be false. This will also be false. So this law here is also perfectly justified. Please, do you all agree with it?
Yes, sir.
Okay. So what we are going to be doing when we are simplifying our Boolean expressions is that you want to manipulate the expressions, okay? Whilst observing all the rules, okay, in order for us to arrive at one of these things, when you're able to manipulate them to arrive at one of these laws, you're able to directly apply the law. Most of the time, you have to rearrange them, use the distributive, commutative properties and those things to rearrange them, associative, to rearrange them into a form where we can easily apply the laws and then simplify them. So when you are solving an example, we look at that properly. So we are also saying here that for this same expression, which is A and A bar, if you have A plus, yes, sir.
Please, I have a question.
All right.
Please, you said the A dot A bar is equal to 0, right?
Yes, sir. A dot A bar is equal
so
to 0.
the A is 1 and the A bar is 0. If I'm mistaken.
Okay, so A is
so
1, A bar will be 0, sure.
So the first one we did, the first one.
Okay, that's
so can we,
this one.
Yeah, yes. So can we say that A dot A is equal to 1?
A dot A is equal to 1. That's not always the case. For example, 0.0 it justifies A dot A, but it will not return 1, but rather it will return 0. I don't know if you're getting. So
yeah.
So A all right, so you will come to other instances, but for A dot A would only return 1 if your A is 1. Okay. But when your A is 0, A dot A will not return 1. Sure, sir.
Okay, thank you.
I will come, sir. All right, so we're talking about A and A complement. So if you have A plus A prime or A plus A complement please, sorry. So if you have A plus A complement, then let us look at this. So A plus A complement is quite different from A times A complement. And this is where the difference comes from. Okay. Assuming you have A to be 1, that means your A complement is going to be 0. Okay. Using the OR operator, the OR operator returns a true if at least one of your input is true. So here we have two inputs, which is 1 and 0. But one of the input is true, which is 1. So that means it will return a 1 using the OR operator. Okay. Assuming A is also 0, then A bar will be 1. Because A bar is the inverted form of 1. If you invert 0, you get 1. If you invert 1, you get 0. Okay. So the OR operator returns a true if at least one input is true. So in this case, you have one input being true, which is this particular input here. That means your output will also be 1. So you see that for this particular law here, with all given combinations, we are going to have a 1. That means that if you are solving any logical expression and you come across any such thing as A plus A bar, B plus B bar, B bar, C plus C bar, or any such instance, then this automatically equates to a 1, or you can automatically replace this with a 1, and you are good to go. If you are to meet A times A bar or A and A bar, you can replace it with a 0, and you are good to go. Okay, so this is what the law is telling us here. So let us look at the third law. We are saying that if we have A dot 1, okay, then we are going to get A as our output. And for this one, it's just very, very direct and very, very simple to prove. If you have an input, which is 1, your A can be either 1 or 0, right? So let us look at all possible combinations. You can have 1.1, right? Or 0.1. We know your AND operator only returns a true if both of your inputs is true. Please, somebody has submitted. So if both of your inputs are true, so that means that this 1 and 1 will give us 1, right? But in this case, what do we see here? Both of our inputs are not true. Only one input is true. So that means that our output will automatically return a false. So we can see that always in all these circumstances, our input is the same as our output is the same as our input. We can see that, right? So our output is the same as our input, which is A. So we just pass on our input as our output. So when we have when we encounter any scenario like A and 1, we know that our output is the same as A. Okay, so sometimes you see this A and 1, you might not always have it as a single alphabet and 1. Please, let's take note. You can sometimes have it as a whole lot of things like S bar, Y, Z, okay, all times 1. The output is still this, okay, like this. Let's take it as let's take an example. Let's say this, okay. So you have X, Y, Z, okay, plus, let's say X, Y bar Z plus X, Y bar Z. Okay, this looks a lot, but then the Boolean laws are telling us that all this okay. Let me make a slide variation to the team right here. Okay, so if we have, let me put a bar on this. So you have X, Y, Z plus X, Y, Z all bar. Okay, the Boolean laws are telling us that all this will return a 1. You are getting me? So you just have to replace 1 with all this, and you are correct. You can just move on. with that. Or in a case where, let's say, each one is complemented, you don't have the bar affecting all of them, but you have X bar, Y bar, Z bar, is still the same. Then the output is also going to be a 1. Okay, so I really want to get other examples, but they are not coming. So let's go forward. Let's go forward. So you have A plus 1 here.
Hello.
Yes, please.
Yes, please. With that example you just gave, I think it will not be so. If
all right, so
because if we say x, the thing you said is x y z plus x y z or bar.
Okay.
If x is 1, y is 0, z is 1. Now,
okay. So your inputs are S is 0, Y is 1, right?
Yeah.
And Z is.
The same we will still get. So x
Yes.
x is 1.
Okay.
Y is 0. Z is 1.
Okay. And then same for here, this place, right?
So now we will be inverting them.
Okay. So you are talking about X bar, Y bar, Z bar, right? Not everything all bar.
As well, how to be. Okay, this thing is. I think we should take that thing carefully, because if we just say it like that, we'll be mistaken. We should take it a bit slow, that aspect.
Okay, I'm coming. So Y bar, Z bar. And so now the problem, so if I get you right, the problem is if this is equal to this, right? I really want to understand your. Okay, so you let me.
You see,
let's test
the rule said.
Mr. Isaac, can I come in?
He said,
yes,
Mr.
please,
Isaac, can I come in?
I think.
All right.
Yes, please continue.
All right. I'm sorry. So, friends, let's just cut it short. So you said remember x y z is a product term, so it means it's a multiplication, and then so is x y z on the other side, just inverted, but it's still a multiplication. Now, if we take into consideration the terms you mentioned, you said x is 0, y is 1, z is 1. This means x, y, z will just give us an output of 0. Don't forget that. Because that's basically 0 times 1 times 1. That's still a 0, right? Mr. Prince, you agree to that?
yes.
Good. Now, if you invert,
yes, I agree.
Good. So if you invert that very term on the other side, what this means is that the product instead of 1 will now become, instead of a 0, will now become a what? 1. You understand that, Mr. Prince?
Take that again, please.
Mr. Prince, if you do x, y, z, and then it gives you a 0, this means the inversion of x, y, z is going to be a what?
Okay, so it's going to be a 1, yes.
Exactly.
Yes.
So what's 0 plus 1? What does it give you?
That's 1. That's 1.
Yes, and that's the reason why this law applies in every instance, okay?
So then he also said back then that x bar, y bar, z bar, that would be different then.
No, it is still going to be, it's also going to be the same thing in the sense that inverting the individual variables will mean that x, which used to be 0, now becomes 1, right? Y, which used to be 1, now becomes 0, and z, which used to be 0, or which used to be 1, also becomes 0. So now you have 1 times 0 is still 0. Do you understand that?
Exactly.
Good. So then that's the individual inversions on this side. You are saying that how is that the same as when all of them are bad? Oh, okay. Is that what you're asking, Mr. Prince?
Yeah,
So,
yes,
Okay, so
yes,
Mr.
that's
Isaac,
my
I
question.
think
That's my
you
question.
see what he's
I'm now
saying now.
getting the question.
Oh,
I'm now
okay.
getting the
All
question.
right.
So initially, I was stuck in between understanding whether
He
probably
was talking about the first,
the
exactly.
whole thing
Yeah,
being one or
exactly. The individual
x
inversions.
bar y bar z bar being equal to x y z all bar. So I think that is the question. And actually testing this with actual figures, I might go with what Mr. Prince is saying. No, please, the name again. The person who asked the question.
I'm Prince.
Okay,
I'm Prince
also.
Abadi.
Yeah, I'll go with what Mr. Prince is saying. I think those two things are not the same. That's x bar, y bar, z bar is not equal to x, y, z or bar. So please let's just ignore that. Okay. So x, y, z plus x, y, z all bar will give us 1. And the reason why it justifies the law exactly is that if you take this here, okay, you can label x, y, z as A. So you have A here plus, no, let me use capital A. So you have A here plus, you have x, y, z bar, which is A bar. So technically, this one here is the same as this. If you decide to say let x, y, z equals A, you arrive at A plus A bar, which is still 1 at the end of the day. So please thank you for drawing a notice to that. All right, so let us look at the other laws or rules. So we said that if you have A plus 1, we've already talked about the AND version, right? So now we are talking about the OR version of that same law. So if you have A plus 1, let us give it live inputs. Okay, so A can either be 0 or 1, right? So we have 0, you have 1. So 0 plus 1, you are still getting a 1. Okay. And then 1 plus 1, if you have 1 or 1, at least one of our inputs is true. So we know our output will also be true. So we know that all these two instances returns a true, which is 1. So we are good with this. So let's look at the next. The next, if you have A times 0, that will give you 0, okay. And then if you have A plus 0, that gives you A. So to justify this, we can just use the inputs. We'll use 1 and 0 as our inputs, right? Our input combinations can only be 1 and 0. So we have 1 plus 0 for this, 0 plus 0. When we are dealing with, or if at least one of our inputs is true, the entire problem there will return a true. So this none is true, so automatically we return a false. Okay, so you realize that at the end of the day, our output is still the same as our input. And then for A times 0, you can have 1 and 0. So 1 times 0, 0 times 0. So we are using the AND logic here. The inputs can only be true if both inputs are true. I mean, the outputs can only be true if both inputs are true. So this is obviously false. This here is obviously false. So we know that the set of all possible outcome here is false. Okay. And now let's look at the absorption rule. And here is what it says. So if we have A plus A bar B, okay, this here we can expand it as A plus A bar, right? Then A plus B. And from our laws previously, we can recall that a plus a bar is going to give us 1, right? And I don't know if you recall that if the inputs, whichever inputs combination that we use, we are going to get a 1 for this. So we have 1 bracket a plus b, and that gives us a plus b as the final output for this. So whenever you have anything like this, you should know that the final answer is going to be a plus b. So that's what the absorption rule is telling us. Okay, so we can now have De Morgan's theorem. So De Morgan's theorems, you can memorize it with this simple strategy. Okay, so you break the sign and then you invert the symbol. That's everything about De Morgan. So if you have a plus b or bar, okay. So what you are going to do is that break the line, okay? I mean, break the line. So the line at the top, just break the line. Okay, so we break the line for each individual members. We have A, B, and then invert the symbol. So we have A bar, B bar, and then invert the symbol. You have or here. So you just invert the symbol to and. So this is the first theorem for De Morgan's. And then the second, we are saying that if you have A times B, we are also going to do the same thing. Break the line, we break the line for both members. We have this, we have this also. And then you invert the symbol. So you are going to have a plus here. So I think De Morgan's theorem is much direct, simpler, and easier to recall. Okay. So the rules we can attempt to apply them. And please let's take note of the commutative and the distributive property and associative. I mean, when we have something like AB, okay, AB would always return is the same as BE. These two will always return the same result. And if we have A plus B is always the same as B plus A, okay? And then if we have A plus B plus C, no matter where we decide to put the brackets, B plus C, we can decide to put the brackets here, we can decide to put the brackets here. They are the same, okay? All right, so because of time, let's move straight forward into solving some practical examples. Okay, so please, the whole thing with this is that when dealing with laws, we are talking about memory here. Okay, you are not really working from your understanding only. You are working with your memory as well. That means that you have to practice a lot. The more you practice, the more they stick. Okay. And the more they stick, the more you can easily record them and identify them in problems and apply them. So that means that individually, you have to look for more problems. I think I'll try after the class, I'll look for more problems and then put them there so that individually we can attempt them. We cannot look at everything because what you are supposed to cover is a lot. After this, we also have to shift over to the Karnaugh maps, okay? And we have to close at 9 also. So we would take as much examples as we can, but I would also advise that on our own, we should also do a lot of work on being able to memorize it all. So let's take our first expression or our function. So we have, let me use x, y, z, okay, plus x prime plus x plus x y prime z. Okay, so we have a very, very simple problem here. And you see, if you attempt to draw a circuit diagram or you attempt to draw your logic gate for this problem set, you end up having something very complicated because you'd have at least one, or this, if you implement this using one logic gate, you have one, you have two, you have three, you have 4, then you have 5. Or if you decide to implement this and this with one logic gate, at least you would have 1, 2, 3, 4. Okay, but we can just simplify this, and then at the end of the day, it becomes much simpler to implement. So let us simplify this. So what can we see here? We can decide to regroup the terms here. Okay, so we send this to this side, and then we can decide to bring this to this side to isolate our x bar. Please, there are different ways you can simplify it. The main aim is that you arrive at the same answer. Okay, sometimes you can decide to simplify it using different strategies. You still arrive at the same answer. I've encountered problems where I've done that with about 2 or 3 different ways and then still arrived at the same thing. So it's not compulsory that the simplification has to follow one rule or style. You just have to be able to work the problem set carefully and identify something that you think you can use to break it down. Okay, whilst at the same time making sure you arrive at the right answer. So for this, the easiest way we can go about it is regrouping our terms. Okay, so we have x, y, z plus x, y bar z all plus x bar. Okay, so from here, what can we do? You know, we can decide to as in factor xz out, right? And then we'll be left with y plus y bar plus x bar, right? So now what we have here is very, very familiar. When we go back to our laws, we said that we encountered a problem like a plus a bar, right? And what did we say about this? We said that when you encounter anything like this, the result is always 1. Okay, so with that said, we can say that y plus y bar is a direct reflection of that same law. So everything here is going to give us 1. Okay, so we are going to have x z all times 1 plus x bar. So all times 1 plus x bar. And we stated also that if we have a and 1 is going to give us a, right? So that means xz times 1 is still going to give us xz, right? Plus our x bar right there. So what can we do to this? We can apply our absorption rule, right? And what did we say about this? We said when we have anything of this sort, we can decide to expand it. Please, the reason why sometimes I prefer expanding it, if you don't really understand the application of the law, please just expand it and then go your way, okay? Else, if you have the bars interchanging positions, you might really mess up sometimes, okay? So here, if you are to expand this, you are going to get x bar plus z, right? And then x plus x bar, right? And you know x plus x bar will give us 1. So that means that if we apply the absorption law correctly, we will have x bar plus z as the simplified form for this, okay? So that means that the simplified version or form of this expression is f is equal to x bar plus z. From here, there is nothing we can do to simplify again. So we recognize that as a final simplified version. Please, are we all okay with what we did just here? Or someone has a question?
Yes, sir.
Okay.
Please, can you
So,
take it from the expansion of the x z plus x bar from that side to the downwards?
okay, please, let's do that again. But please, apart from that, I believe everyone is okay. Okay, if there is someone here who is not okay with what we did, we can go over everything again. Okay, the goal is that everyone understands, not that we complete everything. Because if we are to complete and someone does not really catch up, then the purpose for reassembling is not met. Okay. So if someone is complete with what we did, you can kindly indicate and we'll take it all again. If not, then I'll take it from this particular point. All right, so from this, we stated when we're looking at the Boolean laws that if we have an instance like A plus AB, we can reduce this simply to A plus B, right? We can reduce this to A plus B, okay? But sometimes we encounter a problem here, and a problem we would encounter is with the position of the bars, okay? Sometimes you have multiple, how do you call it, variables having a bar on them and those kind of stuff, and you don't really know how the final result should look like. So I was trying to say that for you not to confuse yourself, you can just use the expanded form, and then you know how your final output of that will look like. So to expand this, we said that you take A, that is this A, so this A times your A bar, okay. This A times your A bar, and then we are going to do this A plus your A bar mean, and you are going to do the same thing with your B as well. So this, we are going to do the same with the B as well. But you know, A plus A bar is 1. Okay, so we'll be left with A plus B. And we know that A times 1 is A. Okay, so if we assume that the whole A plus B here is A, then if we multiply it by 1, we should get this right here. Okay, so that is the exact law that we intended to apply, or we intended to import here. So importing that law, we are saying that this gives us x bar plus c, right? That is this x bar plus z. And then this x bar plus x. So if we have this, you know, x bar plus x satisfies the A plus A bar rule, right? Which is 1 times, you have your x bar plus z. And you know that x bar plus z times 1 will give us our x bar plus z. So that was how we went from this place right to this place right here. Please, are we okay with that?
Oh, yes. I'm okay. Thank you.
Okay, so we can decide to test this here with various inputs to see if we are correct. Okay, if you have the time, you can always decide to test your expression to see if the result coming from that is the same as the answer you had. Okay, that ensures that you've not made a mistake during your working. So okay, so to test this, we can take, please, notes. Okay, let me give this disclaimer. You can, for example, this expression right here has 3 variables, and these 3 variables here can have 8 different set of 8 different combination of inputs. So that means that you can test about 3 different combination of inputs, and your answer will be true. That does not mean you are right. If even one set of inputs invalidates everything, that means these 2 things are not the same. I don't know if you are getting me. If these 2 things are the same, every possible set of inputs should be the same as this. So if you want to test, it has to be rigorous. Else, technically, you might end up, I wouldn't say deceiving yourself, but you end up thinking you've done the right thing, but you might still be wrong. Okay. So to test, let us use 1 for x, then we use, let's say, 0 for y. And we don't really have the time to test all 8 possible combinations. So let's just test like 3. And then for z, let's use 1 and see. So if x is 1, y is 0, z is 1, that automatically is a 0, right? Because you know, when you are dealing with and everything has to be true for the output to be true. If there is even 1 false in it, everything will be false. So that means that this same expression here will also return a 0. Please, we all agree with that. Because our x is 1. If we invert 1, we get 0. So even if 1 is 0 and we are dealing with the AND operator, you know, everything is going to be zeros because we need all our inputs to be true for us to return an output of true. That means that we will only be left with our x bar, right? And our x bar is what will determine our final answer. So our x is 1, so x bar will be 0, right? So that means the whole of this thing, if we are to use the input combination of 1, 0, and 1, is going to return a 0. Let's test with this and see. Okay, so we have x bar will be 0 plus rz. Rz is 1, right? So we are dealing with our OR operator. No, we are dealing with our OR operator. So this returns a 1, which doesn't agree. It doesn't agree. It doesn't agree.
Is Isaac?
Yes, please.
In the solution, that one, the solution, there's a part, the x z plus the x bar.
Yeah.
So can you factorize z out so that it will be with x plus x bar?
I said no, you cannot factorize z. You can only factorize z if you have z here also. You know,
Okay.
to take z out, there has to be z here and z here. Okay. Aside,
Okay.
if that's not much, you cannot
Okay.
factorize out.
Okay.
Okay, so Oh no, yeah. Please, I'll have to look at this again. But I'm very much sure of this answer. Okay. I'm very much sure X bar plus Z is correct, right? It's correct here. But I'll personally have a look at it again. Okay. All right, so let us look at another example here. Okay. So this let's work on it together. So I'll put it out there. We attempt it and then we look at the answer together. So we have A bar, B bar, C bar plus A bar. Let me take B bar. And then we have C plus we have A bar C. Please, I don't know if you can see that clearly. So we have A bar, B bar, C plus A bar, B bar, C plus A bar, C. Okay. So A complement, B complement, C complement, A complement, B complement, C plus A complement B. So please let's attempt it in let's say a minute or two, and then let's see the answers that we would get for that, and then we solve that together.
Hi. Please, can you mention it again? Some of us, our network is not good, so we can't see your screen. So can you mention it again?
Oh, okay. So we have A complement, B complement, C complement, plus A complement, B complement, C, plus A complement, C. I don't know if you got that. A complement, B complement, C complement, plus A complement, B complement, C, plus A complement, C, or A naught, B naught, C naught, plus A naught, B naught, C, plus A naught, C.
Okay, got it.
Okay. Okay, so please, do we have an answer?
Yeah, yes, some are in the charts.
Please, are we together? Hi, Mr. Freeman.
Mr. Isaac,
Yes, please.
I was saying they are in the charts.
Okay. I'm not seeing that. It's okay. Oh, okay. Okay. So we had A bar, okay, B bar, C. All right. So I think Mr. Freeman, your hands are up. Okay, so please, let's kindly revisit this again. Okay, I think I took a thorough look at it and I realized that I did a mistake. Okay, when it comes to testing our inputs, the answer is correct. X bar plus Z is the correct answer. But let us look at the input again. This particular input here is X, Y bar Z. Okay, and our input are X is 1. So that means this X here is 1. Y is 0. So Y bar is 1. Not 0, and Z is 1. So that means that all our 3 inputs will be 1. So this is a 1, not a 0. And that was what created a conflict here. So we have X bar being 0, okay, and we have 0 plus 1. So the final output for this set of inputs will be 1, not a 0. Please, I believe we are all good with that. Please, I believe we are all okay with that.
Yes.
Yes, we are. Yeah, we are okay.
Yeah, sure. So the misinterpretation was in misrepresenting the alphabets right here. Okay. So we can move on and then solve these two together. So we already have the answers in the comment, but let's all work it together. So we have A bar, B bar, we have C bar, O plus A bar, B bar, and then we have C, O plus, we have A bar, C bar. I believe this was a question. So to solve this, we can directly decide to factorize A bar, B bar, right? And then if we are to factorize this, I think we'll have C bar plus C right here, plus A bar, C bar, right? So these two here gives us 1, right? So we have A bar, B bar all times 1, right? Plus A bar, C bar. So this right here gives us A bar, B bar plus A bar, C bar. So what do? We can decide to still factor A bar out, right? Yeah, so someone might decide to factor A bar here, but we'll have A bar plus C. Bar at this point. Please, does that tally with the answers that we had?
I think you solved the wrong question.
I solved the wrong question.
Yes.
Yes,
Okay.
please.
Okay, so please, can you identify that? I think I didn't memorize it properly. Please,
The
where was the difference?
The last one is A bar C, not A bar C bar.
Oh, okay. Okay. But assuming this was it, then this should have been the solution. Sorry. I think this evening I've not eaten, so the brain is not working right. So, all right, so let's solve this again. So we have our A bar, B bar, right? Out, right? So we'll be left with C bar plus C plus A bar C. So C plus C bar gives us 1. And then we have our A bar, B bar, right? So let's just do away with the 1. Since we know A bar, B bar times 1 already gives us A bar, B bar. Okay, so we have plus A bar C. So if we are to factorize, we will have A bar brackets, B bar plus C as our final answer. Idiom. So I believe that is what we all had. Yeah, so we can move on, and probably let's look at one more example before we proceed from there. All right, so the third example, let's look at the function f equals. This a little bit complex, okay? But let's look at it. I believe if we're able to complete this, then so sorry. Let me just take these things out. Okay, so this is our problem. This is our problem. Let's try and then work this out, and then we can now move to look at K-maps. Okay, so please can we try this? I think let's use 2 minutes to work this out, and then we all work it together and move on. Okay. Please, are we done? Or you are still on it?
Yes, we are still on it.
Okay, please. Okay, please. So let's allow 2 more minutes to complete.
Hello, sir. Please, I got up for a bit. Can I see the question screen?
Okay, boys. So I think we have some very nice answers coming in. Okay, so
All right, that's okay. Thank you.
you're welcome then. So I guess we can now look at because of time, we can now solve it. So I think Mr. Freeman is right. Mr. Freeman is right. The final answer, the correct answer is B prime C. So let's solve it together. So first of all, we can decide to expand this right here, right? So if we are to do that, we would get A, B prime C, right? Plus A, B we have A, B not times B, right? Or times D. Okay, so then when we are done with this, we now have A prime dot B right here. And then we put everything in brackets, then we have our C right here. But if we remember our laws, we said that B prime times B is 0, right? So we can say here that B prime times B is 0. So automatically, that makes this entire term here, it reduces it to 0. Please, do you all agree with that? Because B not times B gives us 0. So after that, we are using the AND gate here. And whenever we are dealing with the AND gate, we need all inputs to be true for our output to also be true. So even if one input is true, is false, everything becomes false. So now that we've been able to falsify this here, which is B prime times B, and we know that that is 0 according to our law, then we know that everything here now becomes 0. So this is out. So we now have A, B prime C, right? Plus we have A prime B times
B
C.
prime.
Come again. Oh, sure. I've swallowed the prime. All right, thank you. So we can now continue from there, or we can now progress from there, right? So what again can we do? We can decide to now open our bigger brackets, right? And if we open that bracket, or we distribute our C, what are we going to get? We are going to get A, B prime, C times C, right? Plus A prime, B prime, then we have our C right here. So according to our Boolean laws, we know that if a variable multiplies itself, okay, the return is that same, the return value is that same variable. So we have our C falling back again. So we have A, B prime, C plus we have A prime, B prime, C. Please, any question ask at this point, or we can progress. Please, can you progress? Okay, so let us progress.
Yeah, Mr. Zeke, please,
Yes, please.
are you solving it on the board? Because
yes, please.
Are you okay? So it means I have to log out and come.
Okay, that means you can't see my screen. Please, can everyone else see my screen? Okay, you can
No,
see
it
it
could
now.
be my network. It could be my
Yeah, you
network.
can see your screen.
Okay,
You
then
can see your
kindly
screen.
log out. Oh, okay, thank you. All right, so we can progress from here. So progressing from here, what can we factor out again? We can see B prime C here. We can also see B prime C here, right? So we can factor it out here, right? So we have B prime C, and then what do we have left? We have A plus A prime. And according to our Boolean laws, if you have A plus A prime, what does it give you? This gives you 1, right? So we have 1 here, and then we have B prime C, 4 times 1. So that means that our return value is going to be B prime C. That is the same thing as Mr. Freeman had. So if you work systematically, you would have arrived at this answer. So any question with this particular problem?
Hello, sir.
Okay. Okay, so I believe we are all okay with this. All
Yes,
right,
sir,
so
please, can you hear me?
yes, we can hear.
Okay. My question is how you got that portion eliminated.
Which portion is that's you are referring to this portion, right?
The A, yes, that's right.
Okay, so we now had we now had this particular scenario. Okay, that is A. Let me partition this so that it does not enter. Okay. So we now had this scenario here, which is A. Then we had B, D. Okay, so if you remember our commutative property, we know that AB is equal to B. No matter how we arrange it, the value or the return value is still the same. So we can say this is the same as A times D brackets B prime times B. Please, do we agree with this? Do you agree with this?
Yes, sir.
Okay, so we know that B prime B, B prime times B, or B prime and B now justifies our Boolean law. That says that if we have A times its complement or its inverted value, then the result is going to be 0. You remember this, right?
Yeah, I do.
Exactly. So that means that everything in the bracket here now becomes 0. So you now have AD times 0, okay? So AD times 0 or AD dot 0, however you decide to designate it.
Okay, I see.
Exactly. So AD dot 0 or AD times 0. And if you remember the laws, we said when we have A times 0, the result is always 0, right? No matter what your input is, even if it's 1, if it's 0, it will still return a 0 because you are dealing with the AND gate. The input can only be true, both inputs are true. But here lies the case. One of your inputs, no matter what you do, will be 0. So the final output will always be 0. It's just like multiplying any number by 0. You will get 0. Okay. So that was how come we arrived at the conclusion that everything here, just because of this particular thing you've seen here, the return value of everything here will be 0.
Okay, thank you, sir.
You are welcome. You are welcome. So that was how come we had that. So please, does anyone has any other question, any confusion or anything you do not understand? I'm going to leave a lot of examples on the platforms so that we can also work on it. I think we will try different difficulty levels, maybe from medium to hard, okay? And I believe that as we keep practicing, it would make the law stick, okay? And for me, okay, or from my perspective, the basics of DCIT 103 is being able to recall your number bases, being able to recall your logic gates, the functions, how they work, simplifications, being able to understand your K-maps, okay, being able to, once you have those basics, then you are just, everything else, you are just building on them, okay? But once the basics are not really understood, then it's like building a house without a pillar. Obviously, it will break down. At the beginning, it will look like you are building a house, but at one point or the other, everything will come down again. So let's do to solidify ourselves in the foundation. So let's introduce K-maps and then we end the session because our time is already up. So we said that if we want to simplify Boolean expressions, we can decide. Please, simplifying Boolean expressions are very important. If you have a very if you are working with something and you have a very complex expression, you do not have to end there. The standard is that you reduce the expression to a simplest form, okay? And to do that, we've already looked at how to use a Boolean laws to simplify it. Or you can also decide to use your K-maps, which is your Karnaugh maps, to simplify expressions, okay? So it's a two-way thing. You can use it to either derive your expressions from an already or a pre-existing table, or you can use it to simplify an already given expression. So to use the K-map, you have to understand the basic laws or rules that comes with the K-maps, okay? So we are going to look at the laws, we are going to look at how they work. But first, let's look at the types of K-maps that we have. So to determine the type of K-map that we are working with, we are going to work with, you first have to use or look at the variables, okay? Or the number of variables that we have in our expression, okay? So for instance, if you have an expression like if is equal to B C plus AB, right? This an expression right here. So you ask your question, which K-map am I going to use? Okay, you first have to ask yourself, which variable K-map are you, or how many variable K-map are you dealing with? So first count the number of variables you have in this expression. You have B, you have C, you have A. I've already explained what variables are. So we said variables are all unique members of an expression. So all unique members here are, we have A, we have B, and we have C. So since you have 3 variables, you can say that this particular expression will need a 3 variable K-map to solve. Okay, we will need a 3 variable K-map to solve. So for you to understand what a 3 variable K-map is, it means that if you want to know the number of boxes your K-map should have, you use 2 raised to the power n, where n is the number of variables that you have. Okay, so if you have a total of 3 variables, you are going to take 2 raised to the power 3, and 2 raised to the power 3, we know that gives us 8, right? So you know your K-map is going to look like something like, okay, let me do this right. It's going to look like this: 1, 2. We have 3 right here. Okay, so if we count the number of boxes we have within our K-map, let me just call it boxes. We have 1, 2, 3, 4, 5, 6, 7, 8, right? So that is how to determine which type of K-map you are going to use. You just take 2 raised to the power your number of variables. So assuming the number of variables in your K in the expression is 2, then you are going to need 2 raised to the power 2, okay, which will be a square K-map, which will contain only 4 boxes, or 4 values inside. So if you have maybe 4 different variables, then you are going to need 2 raised to the power 4. Okay, to work with this particular way. So now that you know your variables are A, B, and C, you can now decide to take your input or represent your inputs. Okay, so we can have A, B right here. I think I'll explain these things better, okay, in our next session. And then we'll have C. And we can have C right here. Okay. So another law of our K-maps is that each unit can only differ. Each box here, the value of each box or each input can differ from the other by just 1 bit. Okay, that satisfies a gray code. So the inputs we are going to designate for this would be that of we'll follow our gray code patterns. Okay, so we are going to have 0, 0, 0, 1, 1, 1, and 1, 0. They are pretty fixed, okay, because the intervals are the same. So, and here is going to be 0, 1. Please, we'll talk about this further in the next time we meet on 203. Okay, so we have this, right? And then we have to be able to determine our sets of all possible inputs. Okay, there are several ways to do it, but there are instances where you'll be given. So for instance, with this, you can be given a table and then there are corresponding F values. Okay, so what you have to do is that you look for the input 0, 0, where AB is 0, 0 and C is 0. Okay, that is this box here. You have AB being 0, 0, C being 0. And then you look at the corresponding F value or the corresponding function value. And then you are going to fill it in here. So assuming it's 0, you put 0 there. Then you have where AB is 0, 1. Okay. Let me just illustrate this briefly, then we close. Okay. So we have A, we have B, we have C, because you said the variables are 3. Then we have their corresponding F value. So let's give just some few examples. So we can say when A is 0, B is 0, C is 0, let's say the corresponding value F value is 0. So we have A being 0, B being 0, C being 1, the corresponding F value is 0. Let's say A being 0, B being 1, C being 0, the corresponding F value is 1. Okay, etc., etc., etc. Okay, so we know that set of all possible inputs combinations will be 8, right? So let us look at this. When A, B is 0, 0, we can identify A is 0, B is 0, okay? And C is also 0. That's this particular box right here. Then the F value is 0, okay? When the second box is when A is 0, B is 0, right? But C is 1. So you know you are referring to this box here. The F value is 0. Then the third one, when A is 0, B is 1. Here A is 0. We can see that A is 0, B is 1. Then we have C being 0. Okay, so A is 0, B is 1. C being 0, we are referring to this box. The F value is 1. Okay, so assuming, let's say this is 1, 1, 0, 0, 1. Then that becomes the K map for this function that we are seeing here. Okay, sometimes you can be given the, how do you call it, the map alone, and you'll be told to deduce your function out of the map. Okay, to do that also, we are going to work with different laws, and the laws that we are going to work is that you select all possible combinations of 1. Okay, and there are also laws behind the selection. You can only select in intervals of 1, 2, 4, 8, 16, and the powers of 2. Okay, in that manner. So here you have 1 here, you have 1 here. So this 1 and 1 here, we just do a simple inspection for our inputs. So if you check this and this, you realize that here is 0, here is 1. We cannot accept that. Here is 1, here is 1. So we know B is true, right? So that means we would have a B. Then we trace to our C. We can see that if we trace this to our C, your C is 0, right? But we need everything to be ones. So that means that you take the complement of C, which is C complement, right? And then you come here. So now you are done with this. You come here, you have 1, 1. That is a plus. So we have this or this. So we know our OR gate is our plus symbol. So we take the 1, 1. You trace this up here. You have your 1 corresponding to A, right? So that means A is correct, or A is part of the function. Then we check whether B is part of the function. We can see here is 0, but we know when we take the inverted form of 0, we get these ones here, right? So we know our 0 is a B value. So we invert B, or we take the inverted value of B, okay? But when you compare C to this, we have 0 and 1, right? To 1 and 0, there is no possibility. Even if you invert the values of C, you will not still get 1 and 1. So that means C is not part of the second term. So we can conclude that the function from the K map is B not C plus A B not, which matches exactly with the function from which we deduced our K map from. Okay, so in our next session, we are going to go deeper into K map, and then we'll look at all the rules, how they really work, how to deduce a function out of a K map, how to convert a K map into a function, how to use K maps to simplify your expressions and all those things. Okay, so let's meet again in our next session, please. All right, so please, is there any question? Do we have any question? Else we can close today's meeting.
Yeah, I have a question.
All right.
Please, can you add the F? Yeah, 0, 0, and 1. Can you explain how you got to?
All right, so you said 0, 0, 1. Which part are you referring to?
The F.
The F value.
Yes.
Oh, okay, so the F value or our function value is just the output, okay? So we are referring to the output of the function if we feed it with those set of combinations. So we are saying that if you take this function, okay, and then if you want to determine the F value, take the function and feed it with all sorts of possible combinations, you get your function value. So whenever we feed A with 0, B with 0, and C with 0, we are going to get your F being 0. If we feed it with A being 0, A 0 being 0, B being 0, and C being 1, then our output is going to be 0. I don't know if you're getting me. So we already know our set of all possible inputs for a 3 variable, how do you call it, expression, right? So whenever we have 2 variables, we know you have 0 and 1, 1 and 1, 0 and 0, and then 1 and 0. Right, but when you have 3 variables, you are going to have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, etc. Okay, and you have 8 different combinations. So you take each combination and then you insert the combination into the function. And then when you insert the combination into the function, you are going to get a F value. That's the result you get will be a corresponding F value. You take the combinations, you put it into the function, the result is going to be your F value. So those are the values that you would fill or you feed your K-map with. So whenever you have your K-map without your functions, technically, all the outputs for all the combinations has already been provided in the K-map. The K-map gives you a visualization of all your possible set of outputs and all your possible set of inputs and their corresponding sets of outputs. So you can just see them, and then you can directly visualize how your function should look like. Okay, so if you look at it, for example, you take your 0, 0 here. So 0, 0, 0. So this means the first 0 is your A, second 0 is your B. Okay, then the 0 here is your C. So you now know that the first input is 0, second input is 0, third input is 0. When you come here, first input is 0. The 0 here is your A. Okay, it's your A right here. The 1 here is your B. Okay, so if you have A being 0, B being 1, then this box here is the box where C is equal to 0. So this box here is the box where A is equal to 0, B is equal to 1, and then C is equal to 0. So everything you see there is the function value or the output of those sets of combinations. So that's how you can basically interpret a K-map, please. So the F that you see there, which is a function value, is just the output of the 3 sets or 3 combinations of input, please. And please, have I answered your question right?
Yes, please.
Okay. All right, please. And we'll meet in our next. I think our time is far gone, so we'll meet in our next section, please. Okay.